Well, it's about time. This video is about time. And it's about time I made a video about time. So, what do we know about time? Well, it's measured in seconds, or hours, or days, or years. It feels like it's going forward, right? It definitely has a direction. Throw in something about special relativity and the speed of light, and we're there. I think it's time we go beyond the clock and answer the question of, what is time?
While time is quite the conundrum, we have a much better intuition for what an event is. An event is something which happens at a specific place at a specific time. Like a doctor's appointment, or that time you climbed that really nice mountain, or when you found Captain Mudrock's buried treasure. Without time, events surely would not be able to exist. So maybe this is a good place to start our quest. For example, if I have a doctor's appointment, two things are required: a place and a time. If the doctor only gives me the place, I will have no idea when to appear. And if the doctor only gives me the time, I will have no idea where to appear. So whatever time is, it seems to work pretty hand in hand with space. To reach an event, you really do have to travel through both space and time. So if space consists of 3 spatial dimensions, perhaps time itself is also a dimension.
Okay, so what is a dimension? Well, dimension is a sciencey buzzword that gets thrown around a lot. But within physics, it actually has a rather concrete meaning. I would say that dimensions are the vessels of coordinates. A dimension is the structure wherein coordinates exist. If you saw my video on what are things, you will know I have a soft spot for coordinates. Anyways, when you give something coordinates, it allows you to say how far away that thing is. For example, if I give this dead hiker the coordinates 5, 0, what I'm actually saying is that the dead hiker is 5 units away from me. What I'm not saying is that I killed him. So, dimensions are what allow us to determine distances. And this is such an important revelation that I will state it twice. Dimensions allow us to determine distances between things. Okay, fine, sure. The standing claim then is that both space and time are dimensions. Sure, fine, whatever, but why does time feel so different from space still? I mean, I can freely control how I move around in space, but I'm restricted to going forwards in time, whatever that means. If we truly want both space and time to be dimension, there's got to be something which distinguishes them. I mean, how do we describe this unmistakably unique feeling of time? In order to understand time, we're gonna have to take it one dimension at a time. So let's start with just one spatial dimension. Well, there's not that much exciting going on here, so let's add one more spatial dimension. If we want to calculate distances in this two-dimensional space, we simply have to pull out Pythagoras' theorem. Good old x squared plus y squared equals d squared, where d becomes the distance between that point and the origin. Now, what do you think happens if we add one more spatial dimension? In 3 dimensions, Pythagoras' theorem generalizes to x squared plus y squared plus z squared equals d squared. Neat. So what do you think happens if you want to add time as another dimension? Well, first of all, I cannot visualize 4 dimensions with sticks and fancy graphics, as those are limited to 3D at best. So there's not really an intuitive way of understanding how distances would work in 4D. Well, let's be physicists. I mean, there's obviously a pattern in how Pythagoras' theorem generalizes to higher dimensions. So what if we do what we just did for 2 and 3 dimensions and just add a t term to our distance function? This is similar to how you could add a subscriber to my channel by clicking the subscribe button. Adding t squared is a good idea, but if we did this, we would actually lose this unmistakably unique feeling of time that we talked about, because there would be nothing to distinguish time from space. Time is unique in the sense that I cannot pick its direction at choice, while the spatial directions, well, they're all arbitrary. Is this x, or is this x? It genuinely doesn't matter, and the distance function expresses that by having the x, y, and z contribute equally and indistinguishably in the distance function. If we truly want time to be unique, we simply cannot add its square to the distance function, as then time would be just another spatial dimension. We don't want that. So what do? Well, luckily, mathematicians have got us covered. Because according to the mathematical rules of distance functions, or metrics as they are formally known, if you don't want to add a term to the distance function, the only other option will be to subtract it. So, this is how you calculate distances in 4-dimensional spacetime. This minus sign actually means that the more that we increase t, that is, the longer we wait, the shorter the space-time distance actually becomes, which is weird. I mean, we are used to distances increasing the further away some coordinates are from the origin, so our spatial intuition for distances simply breaks down. The takeaway is that if this minus sign had been a plus sign, well, then time would have just behaved like any other spatial dimension, which we simply know is not true. What? Is that it? Are we done? I mean, there's a lot left on the video. Wait. There is something weird going on with the units. I mean, x, y, and z, they are typically measured in meters, while t is typically measured in seconds. So the units of d squared become meters squared plus seconds squared? That doesn't make sense. How do you add a meter to a second?
Let's think about why this has happened. We grabbed 4 different dimensions, 3 of space and 1 of time, and we just assumed that we could seamlessly combine them into one 4-dimensional structure, when those dimensions represented completely different units, meters and seconds. This is one of the things you have to keep in mind when working with dimensions. They can represent any unit you want. Remember, dimensions are just the vessels of coordinates, and we are free to pick what those coordinates measure. For example, mass is actually a dimension. When I say that your mum is 50 kilograms heavier than the moon, what I'm actually doing is specifying a distance between your mum and the moon in the mass dimension. In fact, any unit of measurement corresponds to a dimension. And this is actually why you sometimes hear people refer to the units of something as its dimensions. But this means that if we want to combine different dimensions with different units, we need to convert them all to one unit. And this is done no differently than how you would convert from feet to meters. In fact, nothing is stopping you from using feet to measure one of the 3 spatial dimensions, as long as you remember to convert them all to 1 unit when adding them together. I mean, the statement 1 meter plus 2 feet makes no sense, unless you know how many feet go into 1 meter.
So, if we really want our space-time Pythagoras to make sense, we need to introduce a conversion factor between meters and seconds. Let's just call it C for a conversion factor. Well, C has got to have the units of meters divided by a second, because the second is going to cancel with the units of time to give just meters. And what is the value of C, you ask? Well, that actually depends on our definition of both a meter and a second. But given today's standards, C can be experimentally determined to be exactly 299,792,458 meters divided by second. That is the speed of light? Yes, this is actually how the speed of light sneaks its way into the discussion about time. Because let me be clear, up to this point, our exploration of time and dimensions has had nothing to do with light, let alone its speed. So it's really, really weird that the speed of light suddenly appears, right? Yes, it is really weird and highly non-trivial. The fact that C happens to be the speed of light comes from a completely different result within electromagnetism, where a calculation shows that the speed which a light wave propagates at just happens to be identical to the space-to-time conversion factor. So it's not really that the speed of light appears in the space-time distance function, but rather that the space-to-time conversion factor appears in the speed of light. So this is how you calculate distances in 4-dimensional space-time, and it's called the Minkowski metric. I claim that it is due to this minus sign that time behaves so weird. This minus sign is, for example, why we're not allowed to travel backwards in time while we're free to move around the 3 spatial dimensions as we want. When you clicked on this video, maybe you hoped that within a couple of minutes you will be able to answer the question of what is time, but I'll be honest with you, we don't really know. What is time is one of those questions that is really easy to ask, but almost impossible to answer. What we have been doing in this video is acknowledging the fact that time is simply unique and showing how to account for its mysticism. Us physicists, we know how time works, but that doesn't really mean we know what it is. Much of my job as a theoretical physicist is actually to work with and understand time. And trust me, there's a lot more to be said about time. But we have unfortunately run out of time. But trust me, this is not the last time you will hear me talk about time. So if you want a good time, you really ought to subscribe. And remember, keep your atoms spinning and your smiles grinning. Thanks for watching.